For years, scientists have known that Betelgeuse was living on borrowed time. A massive red supergiant in the constellation Orion, it has been swelling, dimming, and behaving like a star standing at the edge of collapse. Astronomers expected change, even drama, but nothing prepared them for what the James Webb Space Telescope began to reveal. At first, the images looked familiar: a turbulent stellar surface, glowing in deep infrared, with convection cells rising and falling like slow storms frozen in fire. But as Webb continued observing, the star stopped looking like a simple aging giant and started looking unstable in a far more dangerous way. Massive plumes of gas were erupting from its outer layers. Shock waves were rippling through its atmosphere. Entire regions seemed to brighten and fade as if something inside the star was pushing outward in uneven pulses. It was no longer just a dying star. It looked like a system losing structural control. But the real shift didn't happen in the images. It happened in the data behind them. Every observation from James Webb is far more than a picture. It is a dense stream of raw information: photon timings, wavelength shifts, intensity fluctuations, and noise patterns buried beneath layers of cosmic interference. Most of it is too complex for traditional analysis. But when this data was fed into a quantum AI system designed to detect deep structural patterns, something unexpected began to emerge. At first, it looked like coincidence. Then repetition. Then structure. The AI began linking seemingly unrelated bursts of energy across different time frames. It noticed that fluctuations on the star's surface were not random but followed a repeating sequence. It identified correlations between gas ejections, brightness dips, and internal shock propagation. What once looked like chaos began to resemble a chain of connected events. And that is where things became unsettling. Because the machine wasn't just describing Betelgeuse anymore. It was interpreting it. It appeared to be reconstructing a hidden timeline of internal collapse, step by step, layer by layer, as if the star's final phase was not chaotic at all, but structured in a way that could, in principle, be decoded. For the first time, scientists weren't just watching a star die. They were seeing a possible sequence for how it dies. Betelgeuse is a red supergiant with a violent interior. Its core is no longer producing stable equilibrium. Instead, it is cycling through stages of fuel exhaustion, contraction, and unstable pressure buildup. The outer layers respond slowly, like a delayed echo of internal catastrophe. Webb's instruments captured this imbalance clearly. Vast convection cells rising like boiling oceans of plasma, while shock waves ripple outward from deeper regions. But what the AI added was connection. It suggested that these events were not isolated eruptions, but part of a cascading process. One instability triggers another. One collapse feeds into the next. Instead of random stellar turbulence, the star may be following a precise breakdown sequence governed by physics we are only beginning to interpret at this level of detail. Then came something even stranger. The AI analysis revealed that certain spectral emissions carried repeating signatures, patterns in elemental output that changed in a structured progression. Iron, carbon, oxygen, and heavier fusion byproducts were not just appearing randomly. Their distribution suggested shifting internal layers being exposed in a predictable order. It was as if Betelgeuse was slowly peeling itself apart. Each eruption wasn't just an explosion. It was a revelation, exposing deeper and deeper layers of stellar history. Like geological strata turned inside out by cosmic force. And then the question emerged that no one wanted to ask too quickly. If this pattern is real, how close is the final collapse? A supernova is not a simple explosion. It is a core failure event. When a massive star can no longer sustain fusion pressure, gravity wins. The core collapses in milliseconds, while the outer layers are violently expelled into space. The result is one of the most energetic events in the universe. But Betelgeuse may not be behaving like a perfectly symmetrical system. The AI detected irregularities in shockwave propagation, areas where energy disperses unevenly, suggesting that parts of the star may collapse or rebound faster than others. That asymmetry matters. It could determine whether the remnant becomes a neutron star or collapses further into a black hole. In other words, the final outcome may not be uniform. And if the AI is correct, we may already be seeing the early signatures of that decision forming inside the data. What makes this even more profound is how the two systems complement each other. The James Webb Space Telescope observes reality at extreme precision, capturing photons that left Betelgeuse hundreds of years ago. The quantum AI, meanwhile, does something different. It searches for structure inside complexity that human cognition cannot easily organize. One sees the star. The other tries to understand its language. Together, they create something new, not just observation, but interpretation at scale. For centuries, astronomers have studied supernova candidates by tracking brightness changes and modeling stellar evolution. But Betelgeuse is now being examined differently. Not just as an object in decline, but as a system producing a readable pattern of failure. And that is where things become philosophically unsettling. Because if a dying star can be interpreted as a sequence rather than a mystery, then it suggests that even the most violent cosmic events may follow deeper rules. Rules so complex that they appear like chaos until the right kind of intelligence begins to decode them. The AI didn't stop at surface activity. It extended its analysis inward, attempting to infer what might be happening beneath visible layers. It suggested that pressure waves originating near the core were propagating outward in structured intervals, not random bursts. These intervals aligned suspiciously well with observed surface eruptions. That implies causality across layers, internal processes shaping external behavior in a predictable rhythm. If confirmed, it would mean scientists are not just seeing a star explode outward, but watching a deep internal collapse unfold in a sequence that can, in principle, be mapped. And that changes everything. Because Betelgeuse is not far in cosmic terms. Its eventual supernova will be visible even in daylight on Earth. But more importantly, it would provide a real-time laboratory for understanding how massive stars end their lives. What makes this moment unique is timing. We are not looking backward at a completed explosion. We are observing a system currently transitioning toward one. That means the data is not historical, it is active. Still evolving. Still changing. Still revealing new structure with each observation cycle. And the most unsettling idea of all is this. If AI can extract structure from stellar collapse in real time, then future telescopes may not just observe cosmic events. They may interpret them as they unfold. That transforms astronomy from a recording science into a decoding science. It also raises a deeper question. If Betelgeuse's final moments can be translated into a structured sequence, then how many other cosmic events are already encoded in ways we simply haven't recognized yet? Supernovae. Black hole formation. Galactic collisions. Even the early universe itself. We may not be looking at isolated phenomena anymore. We may be looking at patterns inside a much larger cosmic language. In the end, Betelgeuse remains what it always was. A dying giant, unstable and powerful, nearing the final threshold of collapse. But what has changed is how we see it. It is no longer just a star fading in Orion. It is a system speaking in light, motion, and energy, slowly revealing its final structure. And for the first time, humanity is not only watching that process. It may be learning how to read it.